So, all of those old Soviet landers could only photograph maybe a few square meters of the surface at best at each of a few landing sites. Most of them didn't even have cameras at all. The only way that we can map the entire surface of the planet is by radar. Radio waves are the only kinds of electromagnetic waves that can penetrate the clouds completely, and radar is sending in a strong radio wave and having it bounce off the surface and reflect back to us. What you see here is a reproduction of what the planet would look like if you could remove the clouds and if you were only seeing radar reflections. That doesn't mean that the bright spots would actually look light-colored if you could look at the rock there. It just means that that's where the rock is reflecting radar more intensely. The general rule with a radar image is that a perfectly smooth plane will absorb radar and so look black, but something like a jagged rubble pile will reflect radar very efficiently and will look very bright. So the feature that's a bit below the center of the image here must be a very large section of Venus where it might be very rough and jagged to walk across, and the other areas that appear black would be the smoother plains. No sense of real color of the rock is at all even being hinted at. Just rough versus smooth in an image like this. And why we're showing it to you as orange is sort of an artistic license, since the Venera landers did show that in visible light anyway, only the orange-red colors of visible light are getting through in a way that would make everything look orange if you actually walked around on the surface. But that's just artistic license and nothing more. We can use radar to take a very up-close and finely detailed look at a lot of the surface features. Notice that a lot of the cracks in this image look very, very bright. That means jagged rock lined up in those cracks. And we're getting an idea here how the ground is being deformed by various volcanic or tectonic stresses from the heat from below trying to work its way through to the surface. I'm showing you a feature that's been nicknamed a corona. I think that that word is getting overused in astronomy. I would prefer to just say a deforming blob. But what seems to be happening here is some upwelling of warmer material from the mantle of Venus is melting and deforming a little bit of the crust and making something of a blister. Venus has a lot of these blisters all over the surface. And all of these lines and crinkles are suggestive of a crust that's a bit squishy, that you can squeeze it and stretch it and bloat it out a little bit. It's not very brittle. It's quite flexible. Some of the volcanoes that we've seen on Venus are very, very much unlike any volcanoes that have been seen anywhere on Earth. There's a particular category, here are just 3 good examples, called pancake volcanoes, where the lava comes out in all directions from some small puncture in the crust of Venus. It just simply flows out evenly, making a big circular area around the spot where it comes from. And you can see by the radar bright edges on one side of the pancake volcano on the left there that a lot of stuff rolled down slope and built up at the base. But these pancake volcanoes show that the lava has a very, very different consistency, at least in some places on Venus, than any kind of volcano that you'd get on Earth. This must be extremely runny lava to not really build up a height, but just simply flow out evenly until it's all out there, and not even have a preferred direction of flow, leaving those circles. Here's a somewhat more unusual specimen of the pancake volcano category. It's been nicknamed the Tick. for obvious reasons when you look at this radar image. The angle hides a bit of the three-dimensional height of the caldera that you see in the center. There is a slope down before it starts reaching those funny cliffs that go off to the side. But again, volcanic features here on Venus are often just not looking at all like what volcanic features on Earth would look like. Sort of a side view, three-dimensional rendering is helpful here, although the colorization makes it look very, very melodramatic, and they're sticking with the light and dark from the radar images that are just, again, only suggestive of where the surface is more jagged and more reflective of radar. But yes, the lava just kind of runs out like goop in all directions, and the volcanoes appear to be very, very pressed down. That has nothing to do with gravity. The gravity on Venus is actually just a little bit less than the gravity on Earth. You probably wouldn't notice the difference for gravity. You'd feel pretty comfortable. You'd weigh about 90% of normal on Venus. It could be that air pressure has something to do with this. Since Venus's atmospheric pressure is 90 times Earth, the density of air on the surface is actually closer to water than it is to earthly air. It's sort of in between. If you could have a special heavy environmental suit that would withstand the incredible heat and pressure of Venus and strap on a couple of wings, you'd find human muscle power would be enough to fly. You can almost swim in the air. That might have something to do with why these features look a bit different. Or it could be that the consistency of the lava really is just that much runnier. We have to study the question an awful lot further in order to know. And not all the volcanoes on Venus look weird. I find this one reminds me of Mount Rainier. It's a more classic stratovolcano, built up of much thicker, goopier lava that, well, maybe goopier isn't quite the right word, but you know, a thicker, pastier kind of thing with a lot more air bubbles in it that causes a volcano to build up some actual height. And here we can see specific flows that came from the summit of the volcano down the side. You can, if you take a moment to look at the image, see very specific places where the lava came down, and you've got these rough, jagged, hardened lava that would be, well, the Hawaiians call jagged hardened lava a'a, and the smoother stuff the Hawaiians called pahoehoe. And this looks sort of like a Pacific Northwest regular chain of volcanoes kind of place, or Mount Fuji on Earth, over on the other side of the Pacific. So there is variety, just like there's variety of volcanoes on Earth. Probably it's fair to say that the variety of volcanoes we find on Venus is even greater than it is on Earth. More different kinds, including kinds that I've already shown you that we just simply do not see on our own home planet. Well, this is not a volcano. Notice that it doesn't have a central caldera, it has a central peak. And the crater rim and all the splattered ejecta coming out from that all make it very, very clear that that is an impact crater. Venus does not have very many of these. The total count, I forget the number, but it's a lot smaller than the number of impact craters on most of the other worlds. But what's really remarkable about them is that they are distributed very evenly. They're all quite large. That should make perfect sense for an atmosphere so dense. All the smaller and even medium-sized projectiles burn up before they reach the surface. But you're just as likely to find an impact crater on any part of Venus as you are on any other part of Venus. Contrast that with, say, Mars or the Moon, where there are older surfaces and younger surfaces, and the younger surfaces have far fewer impact craters. Well, same for Earth. We find most of the impact craters on Earth in old continental crust places like northern Canada and Australia. Far more impact craters there because the ground there is older. But on Venus, it seems the entire ground is exactly the same age. It's as if the entire planet was surfaced at once. And that is very surprising for a world as large and we would have expected as complex as Venus. Also notice that the ejecta looks very, very fresh. Remember, this is a radar image where bright means rough and jagged. It's almost as if this impact happened yesterday, though you can see the inner part filled with some sort of fluid, probably lava, after puncturing through the crust to some degree. Again, all of the impact craters on Venus are quite large. But with no erosion over a crater that presumably would be millions of years old, that implies that there is no erosion in general on Venus, and it all makes sense when you consider how slowly the planet is rotating and how dense the atmosphere is. The dense atmosphere makes it hard for winds to pick up much speed. Things move slowly. Recall I said 6 kilometers an hour is the fastest recorded speed by any of the landers. But since Venus rotates as slow as 1 turn every 243 Earth days, it hardly kicks up any circulation. And there is no rain either. Those sulfuric acid clouds are far, far too high for any rain from them to make it anywhere near the surface. We imagine that the sulfuric acid droplets simply dissolve in the far upper atmosphere, and the surface is just boring and motionless. No erosion whatsoever to speak of. So all the craters on Venus look fresh, and there are only a few, and they're scattered everywhere around the planet. By counting up the number of craters, we can estimate how long ago the surface was first solidified so that the impact crater record could show to us. Our estimate is somewhere between 500 million to 1 billion years, which is really quite young compared to the age of the solar system. So let's try putting the facts we have just learned together to draw a conclusion. The crust of Venus is softer, squishier, and seemingly of greater thickness than Earth's crust. Softer being more flexible, bendable, not quite so brittle. It's bent and buckled. You can see signs of tectonic folds everywhere, but it does not have plate tectonics. It seems to be too squishy for that, and probably too thick. It releases most of the planet's internal heat through volcanoes. On Earth, most of the internal heat comes out through plate boundaries, mid-ocean rifts in particular. Plate tectonic action. On Venus, volcanoes are the only way to go. And Venus has many of those, with great variety of form, as you saw. And by counting the number of impact craters over the planet, and noting that the distribution is even and few, it has only been solid for about the last 500 million to 800 million, maybe a billion years. 500 million to 800 million years is our best statistical guess. That's not very old. The entire crust of Venus is barely more than 500 million years old? Well, it must mean that somehow the crust melts down every 500 million to a billion years or so to release the built-up heat from inside.